The facility behind us is not a weapons factory in any conventional sense, but something more fundamental.
In conventional warfare, the kill chain described the sequence of steps from detection of a target through authorization to engage to the physical execution of an attack.
We are replacing human judgment at every step of the kill chain with artificial intelligence systems, performing detection.
The speed advantage it confers over adversaries who rely on human decision-making in their kill chain is not merely tactical.
The next portion of the video will take the viewer inside to see exactly how these systems are created, from their most fundamental. What the viewer is about to see represents the industrial foundation of the autonomous kill chain. The hardware, These silicon wafers are the substrate for the world's most sophisticated AI processing chips. Billions of transistors are laid down.
The circuit patterns being transferred onto these wafers represent the physical realization of the AI architectures designed by the system's engineers. The finished AI chip will contain dozens of distinct material layers, each one deposited, patterned, and etched in the interconnect layers. The AI chips being manufactured here require dozens of metal interconnect layers to connect the billions. This comprehensive testing determines the yield. Only the chips that pass all performance criteria will be cut from the wafer and packaged for autonomous systems.
This data center is the computational infrastructure of the autonomous kill chain's training process. This scale of computing is
The performance of the trained neural networks is fundamentally limited by the quality and comprehensiveness of the training data they learn from.
Different aspects of the autonomous kill chain's decision-making require different types of AI models. This involves both establishing.
The training timeline is a strategic variable. Some models require weeks of continuous computation to reach target performance.
Changes. The performance standards required for deployment in autonomous targeting systems are extremely demanding because the cost of
Position between the distinction between the neural network classification systems and the targeting algorithms.
Translating these judgments into algorithmic form requires confronting assumptions and ambiguities that the rules contain but do not make explicit.
The sensitivity of this translation process is critical. The mathematical form of the threat assessment model determines engagement records.
The importance of sensor fusion to the reliability of the autonomous kill chain, noting that the confidence of a diffused lows. The operational value of an autonomous targeting system is fundamentally dependent on its ability to process sensor data.
Individual component performance cannot guarantee system-level success. Only critical initial cases.
The autonomous platforms shown in the cold open draw on a diverse set of sensing modalities, each providing information that the others cannot.
The optical sensor requirements, noting that the targeting algorithms require optical imagery with sufficient resolution to support reliable classification of the target types.
For Sofridan. The complementary role of radar sensing, noting that the radar provides target detection and tracking capability and
The communication system represents a critical capability multiplier, allowing the platform's onboard systems to access.
Electronic emissions produced by potential targets provide signatures that can identify and classify targets independently of their optical or radar cross-section characteristics.
This integrated system test confirms our sensor integration work has achieved its objectives, demonstrating the significant performance.
The autonomous platforms shown in the cold open are not experimental one-off prototypes, but production systems.
The angular composite construction reflects design choices made to minimize the radar cross-section of the platform while meeting
The all-electric propulsion systems used in these platforms reflect the operational requirement for low acoustic and thermal signatures.
With the flight autonomy system must be capable of operating in GPS-denied environments using inertial navigation and
The modular weapons interface design allows different weapon systems to be installed depending on the operational mission requirements.
This comprehensive system integration test represents the last opportunity to verify all functions before the platform is released for operational use.
The simulation environment step opens with a dramatic wide shot of the simulation center, where an entire floor of high-specification
The simulation environments must be accurate enough that AI systems trained in simulation perform reliably when transferred to real operational conditions.
The adversarial training methodology ensures robust capabilities. The AI agents are trained against adversaries.
AI systems trained only on straightforward scenarios without exposure to the complexities they will encounter in real operational.
This comprehensive performance evaluation is possible because the simulation environment allows thousands of scenarios to be run.
The significance of this transfer test as the final validation gate before operational deployment. Systems that pass.
This activation moment represents the point at which months of engineering work transitions from development to deployment. The intelligence flowing into these displays comes from a network of sensors that includes satellite imagery.
This is the moment when the AI system's trained capabilities are applied to the real world for the first time in operational conditions.
This autonomous self-test process performs pre-deployment checks without human supervision.
The autonomous platforms operate as nodes in a distributed intelligence network, rather than as independent systems.
The transition from development to deployment. The system is now performing the mission it was designed for, and
The formation geometry is continuously optimized by the collective AI to maximize sensor coverage while ensuring the formation's collective resilience.
The classification process in this operational environment is more challenging than training scenarios. Sensor data.
The coordination challenge, noting that the number of variables involved in optimizing a multi-platform coordinated engagement across a complex target array is far beyond what human planners could process.
The tactical significance of simultaneous multi-point engagement. The ability to engage every element of a target array simultaneously prevents any element from reacting to.
The complete multi-platform assessment is available within seconds.
The continuous operational cycle, noting that the autonomous kill chain does not pause between engagements to wait for human review.
Ground-based autonomous systems. While airborne autonomous platforms have been the focus of most public attention on autonomous weapon systems.
The engagement request is processed instantly by the kill chain AI, demonstrating the same speed and absence of human involvement.
The same principles of distributed AI coordination that govern the aerial swarm also apply to ground vehicle coordination.
The integration of autonomous ground and air systems is shown as a coordinated operation. The aerial platforms providing persistent surveillance and
surveillance systems tracking everything simultaneously. The AI network maintains a comprehensive.
The AI kill chain system continuously updates its understanding of the operational environment from the results of each engagement.
This new operational model combines the strategic judgment of human commanders with the speed and precision of AI execution.
Modern tactical engagements are measured in seconds.
Unlike human-operated systems whose performance degrades as the number of simultaneous tasks exceeds operator capacity, this continuous production deployment cycle is one of the most strategically significant aspects of the autonomous kill chain.
In essence, equipment for events. An adversary who destroys deployed autonomous systems does not degrade the kill chain's long-term capability if the production system.
The autonomous kill chain is not a static capability, but a continuously improving system that learns from every
Leveraging fates. A nation that has established this production deployment learning loop has created a military capability that improves continuously.
The trained AI models represent accumulated intelligence that took vast computational resources to develop.
The adversarial dynamic, noting that the deployment of autonomous kill chain systems inevitably triggers the development of countermeasures.
Herein lies the paradox, a system that removes human decision-making from the kill chain, yet depends eerily on human.
The competitive dynamic notes that the autonomous kill chain creates a race dynamic in which each nation's deployment provides operational data.
The most important thing to understand about the autonomous kill chain is not the individual systems that implement it, but the complete industrial and technological.
Modern warfare has always been shaped by the industrial capacity of the nations that wage it. From the mass production of conventional...
This means the decisive investment in military capability is not in weapons production, but in AI research.
The removal of human judgment from the kill chain creates fundamental questions about accountability and compliance.
Nations have concluded that the operational advantages of autonomous kill chain capability are too significant to forego, regardless of the unresolved ethical and legal questions.
The future of warfare will be shaped not by the nations that build the most weapons,